Yeah, thank you. So they've kind of sent me, as the introduction said, as a bit of a tame academic. So I've worked in academia for a long time and now work in industry, and I've been asked to give you an overview for some of the problems that we think are interesting for the academic community as well as for commercial organizations. So does the clicker work? Yeah, fine. So I'm going to come out. Right, there we go. So I know a lot of the people in this room have been involved on this journey, but I mean, EDA tools have revolutionized chip design. I don't need to tell people here because many of the innovations that have been made are innovations that you guys have been involved with. But I think in the modern world, like, chip design has changed the way we live in a really fundamental way. I asked Gemini to come up with a little kind of graphic. It's a bit naff, but you get the idea. We've got many of the functions that we use for everyday life are based on custom ASICs. And so whether it's consumer, mobile, GPU, AI acceleration, automotive, whatever, you've got huge numbers of designs, custom ASICs being made each year, often at advanced node. And that's basically a real achievement of EDA and the community here. And so if I think about what the challenge is, if I can sort of, think about just one challenge, it's the complexity. And so chip designs are becoming more and more and more complicated. They're becoming larger. The requirements from the foundry are becoming more constraining. And we've got to manage all of this complexity while at the same time closing timing and getting good results. And particularly as clock frequencies improve and et cetera, et cetera. So challenges, for me, increasing design scale is a huge challenge. Design's just getting bigger and bigger. I'm going to show the same plot that we've already seen twice before this conference, so apologies for that. 3D-IC, heterogeneous, again, that's a challenge. Making the best of backside resources, and we've just had a talk about turnaround time and runtime. That's a huge challenge. I think our customers rightly say, well, I've got 200 cores. Why do you only scale to 4 cores? And that's a challenge for EDA tools. There's been a lot of discussion about deploying AI. I think that can help a lot. However, I think we're at the start of that journey, and there's a lot more that we can do. It's a really interesting topic for innovation. So, okay. Design scale. So what do I mean by that? So we've seen a huge increase in the size of designs, and it's the size of designs in many different dimensions. So apologies for showing the graph again. But basically what you see is that the number of cores have increased, whether that's CPU cores, GPU cores, AI cores, whatever. And we're now seeing designs which are, hundreds of cores or more. We're seeing huge increases in the number of standard cells, which are that people are trying to optimize to make up your big SoC. And so that's some dimensions, but it's also the number of clocks being super huge, the number of power domains, and so all of the assumptions that we've made for EDA tools, those are constantly being violated. We're constantly being pushed. So at advanced node, we've got a whole load of new foundry checks. I'm going to show you a marketing slide in a minute. Apologies for that. But runtime, memory, algorithmic complexity, all of those things which you guys are really good at, they're all being pushed to the limit by the sheer kind of scale of the problems that we're trying to solve. And so, I think we require some new approaches for that. 3D-IC, that's hugely exciting, but it sort of adds further complexity, so you're getting even larger designs, new constraints, heterogeneous dies, different technologies, so you're going to have different libraries. There's a whole load of complexity there. Okay, so this is kind of where we are on the foundry side. So you see that I'm not going to go through this in a lot of detail, but the point I wanted to make is as we've gone through the technology nodes, we've just accrued more and more complicated checks in legalization, in routing, and whatever, and so that adds extra challenges for the tools to check, to verify, to come up with good solutions which meet all of these checks and still get good PPA. So the traditional solution to all of this is to basically partition the SoCs up. And so, as David was saying, you can basically partition your large design up, you work on these in parallel. If you've got the same component instantiated multiple times, so maybe you can optimize your one CPU and then you can instantiate it 100 times or whatever. So you can have, in principle, significant runtime reductions from that. And you can then combine all of these blocks in a sort of hierarchical fashion. So in principle, that's the case. But actually, the reality of trying to do that is that it's really hard. And so as the number of blocks has increased, I think our customers have really struggled with just maintaining engineering productivity with so many blocks to manage, so many blocks to optimize. There's a challenge for assembling all of these pieces. So it's kind of like, it's not quite like Lego in the sense that you have to assemble it and it's all got to work together. And when you're looking at very high clock frequencies, your budgeting, and that's budgeting for delay, but also for resources, whatever, all of those budgets have got to be extremely accurate. Otherwise, when you put the thing together, it doesn't work properly. So the correlation really matters. Again, I think you talked about this a little bit, the timing correlation at boundaries. When you're splitting your chip up into huge numbers of blocks, then the boundary conditions become important. And then at your top level, or even your sort of hierarchy of top levels, the complexity of that becomes very hard. And suddenly you're looking at hundreds or even thousands of clocks, for example. And again, that's just very difficult. Go on.
There's something to increase the volume.
Okay, is that any better?
We can lift the table.
Oh. I can speak really loudly. How? Right, what about at the back? Is it good at the back?
A little closer to the microphone.
Even closer. Hang on, shall I use the other one?
Oh, you can also use this one.
Please, yeah. Is that any better? That's not any better.
Do it again.
At the back? Yeah? Okay, that's more exciting anyway. I hope you've caught what I've said so far, because I said some really interesting and good things. So, okay. Fine. So then the traditional approach to all of these challenges, basically, is to partition the SoC up into blocks, work on these in parallel, and I've said most of this, so sorry. Top-level complexity, basically. That's an area which is really difficult to manage. You can have hundreds of clocks. You've got your routing resources. You've got to shrink your die. All of these processes go on, and so you end up in this huge iterative flow where you're doing the assembly multiple times. You're adjusting your budgeting. It becomes very difficult for customers in reality. So in terms of the sort of two methodologies which are normally used, the normal one, I think the sort of traditional one is a sort of bottom-up methodology where you basically take your SoC, you partition it by function, you try and do your budgeting manually, you have big Excel tables with all of your constraints, and you just try and keep track of all of this stuff manually, and then learn as you go. You're putting things together. That becomes really difficult. So automation can really help here. So you can do a top-down methodology instead, where you basically start with a flat design, you do some very limited analysis, and you try and derive the budgets that you're going to need during this process. However, as I said, correlation is really important. When you're level, you need basically picosecond level accuracy to do this. And this is an area where I think there's a lot of opportunity for AI-driven improvements. On the front side, we have problems with, for example, congestion. Designs are getting larger and larger, and routing resources are at a premium. And as we go to small technologies, we're seeing more problems with like veer resistance, IR drop, all of those things. And so using the backside as a resource, both for power and also for signal routing, provides you additional opportunities. So this is a sort of typical front-side approach. You've got, I'm going to steal an analogy from Chuck. So when you're building your clock tree, you've got your nets which are going very far across the die. Those are sort of like your freeway nets, and you want to go very fast. And then you have your kind of more local roads, right? And so for your freeway nets on the front side, you've got to end up with these huge veer stacks because you're going all the way down to M1 or M2, up to the critical layer, and then back down again. And you can kind of take a shortcut on the backside. And so rather than taking the direction with the veer stacks, you can basically take a shortcut. You go through the substrate, you take your long route, and then back up. And potentially this can improve your performance. So one solution that is worked on by the group that I'm in is this idea of a flexible H-tree. So we all know what an H-tree is. Flexible one is basically something that's topologically an H, but can vary in shape, so it's still electrically balanced. And we're now able to put the signal nets for the Flex H on the backside as well, so we can redistribute the clock signal all over the die in a very efficient manner, and then just kind of pop up and have the local routing on the front side. So there's an example. I don't want to talk too much about AI because I think feels like we've talked about it a lot. This is again, a marketing slide, but you got to get the idea about how AI can be used for productivity. So this is a simple example of trying to generate your power description. I think there's a long way we can go with this, of just kind of getting that expertise, both for just productivity, but also for debug. As I think was mentioned, EDA tools can be hard to use, and that's because they're so general. So they're kind of like a programming language and a platform in their own domain. And what we often see is that if they're not configured carefully, then you can end up with suboptimal runtime, suboptimal PPA, and AI, I think, can probably help with that quite a bit. So design optimization. We're using the ML techniques fairly widely in chip design already. So reinforcement learning, graph neural networks, etc. They're attractive from first principles. I think, like academia, we also have trouble with having enough training data to make these techniques work at the appropriate scale. And so it's really attractive to have these kind of zero-shot approaches where you don't need huge training data sets. I know we talked yesterday about non-determinism. I am less sure than the panel that non-determinism is okay. I think we're going to have to figure out ways where, applications where having a non-deterministic input is fine and where it's not fine. Because reproducibility is really important for us, and it's also really important for debug. Okay, so hopefully you heard at least the second half of the talk. So EDA tools, they've unlocked a lot of different chip design applications. Complexity continues to increase, and that's basically a real challenge for EDA tools, and it's something where I think academia can help. And we've heard a lot about AI for PPA and designer productivity, and we're at the very beginning of that story, I think, so there's a lot more.
Thank you. Questions, please?
Hi, thank you for the talk. So how the clock gating work in the backside?
Sorry, could you repeat it?
How does clock gating implemented with the backside? by
So
your
at
side?
the moment, there's only power and signal routing available on the backside. So there's not yet a we haven't got logic cells on the backside yet. So does that?
So you need to go up or something. So you need to treat the clock gating like, for example, a penalty on another TSV cell.
So I don't think. I mean, this is still very much a work in progress, but I don't think there's. So what you can see is that you've got your time critical nets on the backside. The standard cells are still on the front side. I don't think there's any particular reason why you couldn't apply that to cells which are clock gated. So in that sense, I don't think that that's totally viable. However, the backside resources are pretty limited, and so it's about trying to trade that off and make sure that only your most critical nets are available, are using up those resources. And so clock gating, again, it depends on your structure, but you typically have many thousands of those.
Okay, got it. Thanks.
Thanks for the talk. For your tops-down hierarchy generation, can you talk a little bit about your trade-off between the quality of results and the turnaround time?
Sure. So I think probably the ideal trade-off is to do everything flat, right? I think that's reality, is that you're going to get the best possible results in a completely flat net list where you optimize globally, optimally, but realistically that's not viable. I mean, in terms of like the RAM requirements, for example, to run Innovus on some of these very large designs, we're seeing, infeasibly large RAM requirements. So we've certainly bought machines with, multiple. I feel like I've been cursed. Anyway, so the RAM's really hard, the runtime's really hard. So I think, although that's the ideal, that becomes unviable as you go to really very large designs. In terms of the trade-off about how many partitions you make, and clearly the more partitions you make, the more trade-offs you make on the PPA. And we're trying to minimize that. So there is clearly some optimal value. I wouldn't say that we know exactly what that curve is yet. So.
Do you have a specific tool to help people do this, or is it just a giant spreadsheet?
So I think historically it has been a giant spreadsheet. We do have a specific tool. So it's now built into Innovus. We have what the marketing department would call a smart hierarchy flow. And that's able to do a lot of this budgeting and planning for you. We've put a lot of effort into it. But yeah, I mean, it's still, I would say, a work in progress. And I think the challenge really is doing it as a one shot. And so having a flow that might take 30 days to run by the time you've broken up all your blocks and you've optimized all of the blocks and whatever. And so you can figure out all of these parameters, but if you get it a little bit wrong when you put it all together, the results aren't that good. And so I think you end up having some amount of human feedback even so. So you've still got the automation, but I think you have to make the human feedback easy as well.
Okay, let's thank the speaker.